Pleasure to announce the talk of Rodica Dinu from University of Konstanz on the geometry of Gaussian graphical model of the cycle. Yes.
Thank you very much. Thank you for giving me the opportunity to present my work here. I will present several papers that are written together with Carlos Amendola, Mateusz Michalek, and Martin Rodica. Okay, and the plan is the following one. I will start talking about some, let's say, setting from algebraic statistics. Then we turn everything to geometry. So we jump to geometry. So to linear concentration models and the invariants that are interesting there. Then I will restrict myself to the Gaussian graphical models and even the restriction of the restriction, namely I will go to the cycles. Okay, and we will be interested in two invariants about these models. Okay, so let me start saying that a multivariate Gaussian distribution is determined by a mean vector mu from R to the n and sigma, a matrix which is positive definite, and this is called the covariance matrix, and its inverse, which is denoted usually by K. This is also positive definite, and this is called the concentration matrix of the distribution. Okay, let us fix L, a linear space of symmetric matrices that contains a positive definite matrix. A linear concentration model will be given by the covariance matrices sigma such that the concentration matrices, the corresponding concentration matrices are in our space L. And let me denote this by lambda L. Okay, so formally we still require that both sigma and K are positive definite. And we have two important invariants for this kind of models. One of them is the degree of the model, yeah, which is the degree of the variety. Let me denote it by L inverse. So this is the closure of our model in the ambient space of and by symmetric matrices. Let me note here that this is also the closure of the inverses of all invertible matrices in our space. And the second one, this is the ML degree of the model. And this comes from statistics. And a common problem from statisticians is the following one. Given some data obtained after some experiment, so coming from a probability distribution in a model, estimate the parameters that best explain the given data, the observed data. This is usually done by maximizing the likelihood function, so computing the maximum likelihood estimate. And the complexity of finding the maximum likelihood estimate is measured by the maximum likelihood degree. Okay, so if you want a formal definition, So for general data, let's say D1 up to some dk, let's say with mean 0, so mu is 0, the ML degree is the number of complex critical points of the log likelihood function. Should I write it?
Yeah.
Okay, perfect. So sigma goes to log of the product from 1 to k of f sigma 0 of x. And here comes the fun. F sigma 0 of x is determinant of 2 pi sigma to the power -1/2 times the exponential of -1/2 x transposed sigma inverse x. Okay, it will not be that relevant for us anyway, but here is the log likelihood function.
What's the relevance of these?
DIs is a data, the observed data I mentioned before. Some vectors from R to the n for us.
Does it enter the log likelihood function?
Sorry?
Does it enter the log likelihood function?
Yeah, you evaluated at X and it should be D, or is it?
Sorry. Yeah, sorry. Here should be DI. My mistake, yes.
And X is also these.
Yeah, you can plug in here the DIs.
Yeah.
Yes, yeah. Okay, so if no condition is required on sigma, then it means that L is the whole ambient space. One can check that this special matrix, sigma hat, which is 1/k sum of DIs, DI transpose, this gives an optimal solution for our maximization problem. And this is special, and it is called the sample covariance matrix. Okay. But this happens because, first of all, if L is the whole space, it means that in particular the sample covariance matrix is there, of course. But what if the sample covariance matrix is not in our model? Which sigma L hat, which sigma L from our model maximizes the likelihood function, the log likelihood function. Well, for this, there is a very beautiful geometric answer. I said that I will pass to geometry at some point, right? Here is the point. There is a theorem due to Barndorf, Nielsen, saying that there exists a unique positive definite matrix. Let me call it sigma L hat in our model, such that for any matrix in our space, we have the following equality on pairs, namely K sigma L hat is equal to the pairing between K and our sample covariance matrix that is not in our model, And this pairing means taking the trace of the product of matrices. So in particular, in other words, this says that sigma L hat minus sigma hat, it belongs to L perp.
Could I ask the
Yeah.
notational confusion about lambda L versus L? So L is a linear space of matrices that contains a given positive definite one. And what's lambda L?
Lambda L is the linear concentration model, which is here.
Ah,
Yeah, sorry, maybe I should let this like. Okay, good. So we are here. Yeah. So since we have this difference in L perp, this means that it makes sense to consider the projection pi from S2 to Cn, so the space of symmetric M-tensor matrices, to this one portioned out by L perp. And it turns out that the maximum likelihood, the maximum likelihood maximization problem is related, let me write like this, is related to look at the fiber of the map by restricted to lambda L, the closure of it, over the sample covariance matrix. And indeed, there exists a positive definite matrix in the model, in the fiber, and that's exactly the maximizer of our problem. Okay, but the question is now, what about other points, probably complex, that are in the fiber? And here comes a beautiful theorem. This is due to Amendola, one of my co-authors, Gustafsson, Kathleen, Marigliano, and Anna Ziegel, saying that the cardinality of the fiber for general sample covariance matrix is precisely the diagonal degree. So in particular, if you want, the ML degree, I can see it as being the degree of the map from the projectivization of our variety to P of S2 to Cn modulo L perp. Okay. Good. What I would like to add here is the fact that the ML degree of a model is always upper bounded by the degree of the model. And equality holds when we have this intersection to be empty. And by a theorem of Tessier, this happens only when L is general. and fails for special egg. Now, from the statistical point of view, general models, but also special models are of interest for them. And one that, yes.
This last condition, is this saying something about all the other points in the fiber being in the boundary of being semi-definite, not positive definite? What happened to what's happening at the boundary?
The boundary,
You took lambda L,
yeah,
and you closed it.
Zariski closure.
Zariski closure.
Okay, that does a lot of things.
Complex.
First of all, but it also adds, I mean, you're looking, I mean, also getting the boundary of the positive semi-definite, you're getting the PSD cone, and then the complex. But I'm trying to understand the theorem that, what is that, someone in Nielsen? That there's just a unique positive definite matrix.
Yes, unique positive definite matrix.
And a lot of others.
Okay.
Okay. Good. So I was saying that of particular interest are the Gaussian graphical models. Where a graph encodes the space. And for us, L of G, where G is a graph, it will be given by those sigmas such that they have zeros on all diagonal entries whenever there is no edge between I and J, and I is different than J. Note that we always allow arbitrary diagonal entries. So in particular, you can consider loops at every vertex of G.
There's no edge, but I do not.
I and J? Ah, not an edge. Okay. As I said, we are interested in these Gaussian graphical models, and we are interested on this invariance, the degree and the ML degree for these models. And it turns out that even for simple graphs, these invariants are highly non-trivial to compute. And I would like to state now two conjectures. The first one is due to Sturmfels and Caroline Uhler from 2010, saying that if G is an N cycle, the degree of the model is given by the following formula: n plus 2 over 4, 2n choose n, minus 3 times 2 to 2n minus 3. So this is the degree. And another conjecture, this is due to Drton, Sturmfels and Sullivant from 2008, saying that again for the same kind of graph, the ML degree of the model is equal to 1 plus n minus 3 times 2 to n minus 2. Okay, and we will play with these conjectures till the end of my talk. Okay, but before passing to the first conjecture and saying how we prove it, let me tell you also some other interpretation for the degree and the ML degree. So the map from the space of symmetric n-times n matrices, which is given by inverting a matrix, is in fact, it is also the gradient of the determinant. And we have the following commutative diagram. Here we have our map phi that we already know. S2 to C to D and modulo L4. Let's start. Okay, what we have here is the gradient of the determinant restricted to P of L. And here we have a diagonal map, which is the gradient of the determinant restricted to P of L. And in particular, I can read, let's say, the degree of our model by looking at the last integer in the multi-degree of the graph of the diagonal map. And my ML degree, this is the last integer in the multi-degree of the graph of the lower map from our diagram. Okay. Good. I will not use these things, but I felt like it's really nice to see. Okay, and now let's pass to first conjecture, degree of LCN, where SCN is the n size. How much time do I still have?
Slightly above half an hour because we started later.
Half an hour?
Yeah.
Is that short or long?
Short. Okay, then about the degree. Good, so we have a variety. We want to compute the degree. One way of doing this is by computing, by intersecting it with dimension of X general hyperplanes. Okay, so this implies some intersection theory, and the question is where to do it. A naive approach try to do intersection theory in the space of symmetric matrices. But here I wanted to tell you a beautiful story, but unfortunately I don't have time. But I will resume to tell you a nice example, which is the Steiner's conic problem. And the question is the following one. How many smooth conics are tangent to 5 given conics? And the Bezout bound says that this is the number of intersection points of 5 generic degree 6 hypersurfaces, and this is 6 to the 5, which is 76 points over C. However, in this counting, double lines are allowed. So it's not a fair counting. And we know that the number of non-degenerate conics that are tangent to 5 conics is in fact 32 to 64. Okay, okay. I will not explain too much about this, even if I wanted very much to tell you about the story behind this. But it seems like there are problems. And we don't get the right numbers. And this is bad. So this means that we should come up with another idea. And basically what we will do intersection theory in the space of complete quadrics. Okay, and now guess what I didn't write on the board. Okay, let me tell you another story. Till that. This idea of using the complete quadrics is an idea which was initiated by Mateusz Michalek, Monin, and Wisniewski. And this is very much inspired by the work of Juni Ha on relations among chromatic polynomials and degrees of reciprocal linear spaces. Our point of view on the linear spaces representing the matroid in Juni's work is to consider those as subspaces of diagonal matrices while we work with symmetric matrices. And this provides an analogy between the construction of the permutahedral variety and the variety of complex complete quadrics as a blow-up of matrices in loci of low rank matrices. And so far, the variety of complete quadrics was used to provide information only for generic linear concentration models. And from the point of view of the cohomology, this is easier because one obtains transversal intersection and expected number of intersection points. Okay, and just as matroids, special type of matroids give rise to special subvarieties of the permutahedral variety, special linear concentration models give rise to special subvarieties of complete quadrics, but the space of complete quadrics is the variety of complete quadrics is not toric, contrary to the permutahedral variety. So in particular, most of the combinatorial tools that are applicable for matroids will not be available for us. Okay, and now I should write a definition for complete quadrics that I didn't want to be honest, but let me consider V an n-dimensional complex vector space. And the space of complete quadrics is in fact a compactification of the regular symmetric matrices. But let me write one definition. The space of complete quadrics, and I will just write CQ, is the closure of the space of symmetric regular matrices. Okay. And the map phi is given okay. here I take all I by I minors. Yeah. So okay, so this is the map. I wish I had also the second definition and I don't have to write it now, but let me do it because we will need it. And the second definition of the space of complete quadrics is seeing as the successive blow-up of PS to V Okay, now let me explain because I know that I went very fast. The idea is the following one. You blow up rank 1 matrices, then rank 2 matrices, and so on. And this is done by once in the first definition. And this is equal to the iterative blow up, which is presented in the second definition. And D1 here is the locus of rank 1 matrices, and the DIs are the strict transforms of the space of symmetric matrices of rank at most I from the previous blow-ups. Okay, and there is a very nice way of seeing this in a schematic picture that I'm afraid I cannot show it now. So I should finish at 10 after 12. That's bad. And I also need to erase some words.
I
Okay.
can help you with erasing.
Then I can make a picture while Marta is helping me. So imagine that we look at maps from V to V. Here is the zero space, and here is my space V. And if you have a regular map, its image will be V. So basically you go directly to V. So again, this is a schematic picture. It's not meaningful. But if you have a singular rank R matrix, then the image will be in the space of all R linear subspaces of V. So this means that this will be a point in the Grassmannian RV. Yeah. Okay. So if I have a singular rank R matrix, I will jump here. Okay. Then here, until here, if you want, is the space of symmetric matrices. Yeah. But if I want to complete and to go to the space of complete quadrics, I have to see what I will do from this point. Let's see that this is a U. And this U has to be a subspace of V. And now I have a matrix here, and I have a point here, and I blow up this point. And if what I get is the image will, so if the new point is regular, I will jump to V and my journey finishes. Or I will jump to another Grassmannian. I don't know, SV. And I continue this in that direction and so on till in the end I reach the space V. Okay, I think I went too fast, but what I want to say is the fact that the space of complete quadrics is given by all the zigzags. Yeah. that I showed to you. And the blow-up construction can be seen quite well, because if you have a regular matrix, there is nothing to be done. If you have a singular rank R matrix, then you don't go to V, but you land in a point in a Grassmannian, and then you blow up and then check if it's a regular point, then jump to V, otherwise you end sooner, and so on till you reach the end, which is V. And basically it means from this point here, it means by continuing with the map from the quotient V over U to V. Okay, and still a generic point in the complete quadric space is a regular matrix. So it means that you miss all the Grassmannians. Yeah, so these kind of zigzags are only for specific points in the space of complete quadrics. Okay, good. Thanks a lot. Good. And now I want to recall you that what we want to compute is the degree of LCM inverse. And we want to show that it's in fact the formula hidden somewhere there. Here we show something more general. So if you have gamma an arbitrary graph, then the degree of L gamma inverse is the intersection between the strict transform of L gamma with the divisor Ln minus 1 to dimension of L gamma inverse. Okay, and now I realize that I jumped a very important step, and let me tell you what are the LIs, the Ln minus 1 in particular. So we have two kinds of divisors in our space. One of them is given by the LIs, so L1 up to Ln minus 1, and these are pullbacks of hyperplanes under the projections Pi. And the second type of divisors is given by, if we consider E1 up to En minus 1, these are the strict transforms of the exceptional divisors from the second definition. This is why I needed to write it. Okay, and let me tell you here that a general point in EI maps by pi1 to a symmetric matrix of rank I. Okay, and let me denote by S1 up to Sn minus 1. Yeah, this is how I denote it. These are the classes of the E1 up to En minus 1 in the Chow ring of the complete quadrics variety. And in particular, if you want to go back now to our beautiful picture, the SIs are given by all the zigzags that break in a Grassmannian. So in particular, S2 is given by all the zigzags that break in the Grassmannian G2. Yeah, and the intersection of all the SIs is given by all the zigzag that breaks at every Grassmannian. Okay, so we have this nice formula that I already wrote. Okay, and we tried to compute, so this takes place in the cohomology of C2 of V. We tried to compute this intersection here, but it seems to be very hard to be done directly. And what we did was to use some relation. I might have them somewhere. Aha. So in the Picard group of CQV, there are the following relations. SI is minus L minus 1 plus 2 Li minus Li plus 1. So by using this relation in the Picard group, I can express the Ln minus 1 in terms of the other divisors, in terms of the SIs. So instead of computing one term, we computed many more, but in fact, most of them are zero. This is the magic. And we remain with only two types of intersections that are non-zero. And those types are these two that appear here. Okay. They look bad, I would say, but this is what we got. And somehow I should also add that Qn here is exactly the formula that we want, which is n plus 2 over 4, 2n choose n minus 3 times 2n minus 3. Okay, so long story short, we got two types of divisors. We were able to compute them, and we go to these numbers. And I should mention here that there is a lot of intersection theory behind. I mean, one is to understand when you intersect the class of the strict transform with E1 to E1, E2 to an arbitrary ER, what you get, and so on. In order to compute all these numbers here, and we had to compute all of them by ourselves because there was no such things already done for our particular model, of course. Okay. And I want to add also the fact that when you intersect the strict transform with Sn minus 2, so we are here, Sn minus 2, that one is birational to the Grassmannian. So things become easier because instead of doing a general intersection in the space of complete quadrics, you do it in the Grassmannian. And things are there much more easier because we know what's the towering of the Grassmannian. So things go a bit, things go easier there. Okay, so this is how we got the first conjecture. And now I still have like 10 minutes to spend it on the ML degree conjecture. Okay, so ML degree. So as we discussed at the very beginning, the ML degree is given by the degree of the map, rational map from the projectivization of LCN inverse. I will write LCN. I will write it like this right now because I will have upper indices and it will be ugly. Okay, to S2CN helper. Okay, and this is in fact the number of intersection points of LCN inverse intersected with S plus L perf, the base locus, with S is a generic matrix, generic point. Okay, and more generally, this is the number of intersection points of LCN inverse intersected with S plus L perp for any matrix S, providing that the intersection is transverse and the fiber over the matrix S in the graph of pi doesn't contain any point from the base laws. Okay, I will not write this story, but this is what we want. So in particular, we would like to do a choice for S and then try to look at the intersection, see what points are there, if the intersection is transverse, blah, blah, blah. And the most natural choice, I suspect, would be to take the identity matrix. Okay, but now we have to look how the points in LCN inverse, where we have identity plus L perf, how the points look like. And I have everything I need here. Almost. Let us consider Dn plus 1 be the set of diagonal matrices whose diagonal entries are plus minus 1. Okay, this is the group under multiplication, and it seems that our intersection LCN inverse identity plus LCN perp, this is invariant under the action of this group, and this group acts by conjugation on the space of symmetric matrices, so it does here. Good. And what we will do is the fact that we will try to characterize the points that lie in the intersection with respect to the group action of Dn plus minus. And one first step would be, for example, to understand what are the singular matrices in our space. And here we have like two nice results. If n is odd, there are no singular matrices in our space. LCN inverse. Okay, and if n is even, we have some points, and these are done by d Cn times d. The inverse of any matrix from this group is the matrix itself. Okay, where d belongs to Dn plus, and Cn are the checkerboard matrices. So this is 0 if I plus j is odd, and is 1 if I plus j is even. Okay, And in order to give the intersection points, I need some notation, and in particular, I have two types of matrices, let's say. Here I didn't have space to write, but to get this matrix, I will just put minuses here in the previous one. So I have minus in those two corners. Okay, and magic, these are the points. Here I should mention the fact that from this matrix, if we take the determinant, this is a polynomial, and this polynomial satisfies several relations, recurrence relations, and this is why those kind of relations involving P appear in our points. This is not easy, so in particular, I cannot do it in like 2 minutes to explain everything what is here. But the thing is that we got all the points, and if we count them, the number we get is exactly the one conjectured by Drton, Sturmfels and Sullivant, and is this one. Yeah. What I can say, for example, that one comes from the identity. Or, for example, we can try to do a count for the odd case. Because in fact, the stabilizer of this matrix with respect to the group action, this has 2 elements, which are the identity and minus the identity. And then when you take the orbit, this has two n elements. Okay, and we need also the roots of the polynomials. So the cardinality of this set will be n minus 1. And this is a nice thing. This is a nice thing. I can tell you the roots of the polynomial. So Pn of x has simple roots given by the following formula: 1/2 cosinus of a of p over m plus 1. Yeah. Okay, and the counting, at least for the odd case, it seems to work. For even, it is harder. Okay. And okay.
Thank you. Do we have questions?
Yeah, please.
Do you know how they conjectured this number?
Very good question. In fact, I am very curious because, for example, for this number, for this formula, by computer, one can compute, I don't know, 4, 5, maybe 6. Yeah, for 4 cycle, 5 cycle, and 6 cycle. And how they got it, I don't know. I mean, I suppose that they used some trick, right, to get the formula. But to be honest, I don't know.
They don't have. The way,
No.
the way these Sturmfels paper usually, like, there's a huge table of.
But that table has 4 entries. That's
Doesn't sound like a huge.
Does the 3 cycle?
There is a table, but it's not like a huge one.
4 entries, okay.
I don't know if 4, I mean, that's an example of a small integer.
Is one of those numbers the Jonquière number of complete conics?
Sorry, once again.
Is one of those numbers for a given, for small n, is it 3264?
No.
Okay.
In fact, it's not related. It was just an example of.
Oh, it's a different intersection too.
Yes, it's a different intersection. Yeah, I just wanted to show that the intersection theory in the space of symmetric.
If n is like 2
Yeah.
or 3, the complete quadrics is the space that you do that that you solve that problem on. right?
Exactly,
But it's-
exactly, in the space of complete quadrics, yeah.
I'm sure Rodica would like to tell us more. Maybe I will just have a comment that, of course, determining all points in principle for such problems is usually not enough. One needs to
Yeah, this is what I said
Yeah.
at the beginning, yeah. We had to show also the smoothness of the points, and this was
and for the
an easy
first
task.
and for the first result, Rodica said that I mean it's not easy because there was no theory of intersection thing. And the thing is that if you take the strict transform of a specific model, it's not like in matroid theory that it makes sense to ask what kind of intersection of divisors it is, because it is not an intersection of divisors. So you have to somehow really work with the geometry of that. Right. Further questions? If not, let's thank Rodica.